I'm the product manager here at the MathWorks for our computational finance products.
Also with me today is William Mueller.
He is a developer on the econometrics toolbox, and he will be discussing co-integration today in great detail. So here's the agenda for today. I'm going to start out by giving a brief overview of what's new in this release of the econometrics toolbox. I'll then pass the ball over to Bill, who will be discussing co-integration analysis and modeling. And at the conclusion of his portion of the presentation, I'll come back and show an example application of using co-integration to identify a pairs trading opportunity. And then we'll conclude the webinar with a question and answer session. So today we're going to be discussing the new capabilities in Econometrics Toolbox, specifically those in the R2011A release. Now, for those of you who are not familiar with the Econometrics Toolbox, it's used for econometric modeling, time series modeling. In some cases, it's used to develop trading strategies, such as the pairs trading strategy I'll be showing later. And in some cases, it's used to do time series or volatility modeling, which is useful in developing pricing or valuation methods for derivatives. Now, this presentation will not discuss the toolbox capabilities in its entirety, but it will focus on this release, and specifically, we'll be discussing how you can test for co-integration and build models taking it into account. So this slide lists the new capabilities in this release, and Bill will be discussing them during his portion of the webinar, so I won't run through them in great detail here. So at this point, I'm going to pass the presentation over to Bill and let him give you an overview of co-integration and these new capabilities. I'll then be returning at the conclusion of his presentation to show you an example application with pairs trading.
Hi, I'm Bill Mueller. I'm a developer for Econometrics Toolbox, and I'm here to tell you a little bit about a group of new features that we have in the 2011A release of Econometrics Toolbox for co-integration analysis and modeling. To get started, let's look at an example of some data. We're going to take a look here at some interest rates over a long period, about 40 years, for government bonds in Canada. You can see here we've got plotted short-term rates in blue, medium-term rates in green, and long-term rates in red. And if you just take a look at this data, you can see that it has several characteristics that you'd probably expect of interest rates. First of all, the long-term rates are generally larger than the short-term rates, with the exception of a couple of inversions that you might notice at the beginning of the 80s and the end of the 80s. That sort of property of these time series, that one is larger than the other, is something you would typically capture in a mean model for the different series. You also probably can tell that these series are highly correlated, which means that at any particular time, the interest rates tend to either move up or move down together. That kind of relationship is something that you would typically try and capture in a covariance matrix among the three time series. There's something else going on here, though. If you take a look at this, it appears that this data may not be stationary. It does seem to have a bit of an upward trend, at least over this period of history. And there does seem to be some heteroscedicity here. So it's not clear that we're going to be able to model this as a stationary process with a stationary mean and covariance. The thing we want to look at is that over this long period of history, these three rates, as you might expect, move along pretty much together. They seem to stay with each other even as they spread out and come back together. It's not that they're reverting to a particular mean over time, something that a stationary process would do. It's not that they're reverting to a deterministic time trend, something that a trend stationary process would tend to do. But rather what we see is that there seems to be some kind of invisible stochastic trend between these three variables that the three variables never stray too far from. And it's that characteristic, it's that behavior that we call co-integration. And what I want to show you is how we can identify that in a system of time series and then how we can model it. So just to get on the same page with some terminology, any single time series, y sub t, we'll say is integrated if we can bring it to stationarity through differencing. And the number of times we have to difference the data to get stationary data we call the order of integration. We're going to be looking here mostly at variables that have order of integration 1 or 0. So either it takes one difference to bring them stationarity, a typical unit root process, or they're already stationary. In the second paragraph here, if we have a vector time series, y sub t boldface there, with n different components, we say that the time series in this vector process are co-integrated. If there's some linear combination of the individual processes, that's stationary. Typically, we're not interested in having any of these series be stationary individually. That would lead to kind of a trivial co-integration where I could make one of the betas in this linear combination 1 on the stationary variable and 0 on all the non-stationary variables, and that would give me a stationary combination that's not very interesting. Typically, we'll be interested in, for purposes of this demo, I of 1 variables that when you form the linear combination, you get an I of 0 variable. And we're going to think of this linear combination as a new variable. So we start with the levels data, and instead of the usual strategy of differencing the data to form a new variable that's easier to model, we're going to think about forming this linear combination to get a stationary variable that's easier to model. And this combination of variables that forms a stationary process we're going to call a co-integrating relation, and the vector of coefficients that gives us this combination we're going to call the co-integrating vector. So let's take a look at this data in MATLAB. I've got a script here that we'll have available on MATLAB Central. We have this Canadian data that ships in the econometrics toolbox. You can load it up, and we'll just peel off the last 3 variables here, the last 3 columns of the data. Typically, we're going to arrange our data where the individual time series are the columns of y, and the individual observations are represented by the rows. So these last 3 columns in this data are the short, medium, and long-term rates that we just looked at. And then this is just a plot command that will format to reproduce the figure that we just saw. So I'll evaluate this cell, and there we see the potentially co-integrated data that we looked at before. Now, typically in a co-integration analysis, the first thing that you want to look at is the order of integration of the individual variables. Like I said, if one of the variables is stationary, you usually don't want to include it in the analysis because it's going to lead to trivial sorts of co-integration. What we'll do here, just to illustrate, is we'll strip off just the short-term rate. We'll take all rows in the first column of our data. That's our short-term rate. And then we're going to run a couple of tests to see whether this data has a unit root, first of all, right here. And secondly, as kind of an inverse of that, we're going to run a test to see if the data is stationary. When I'm talking about a unit root test or a stationarity test, I'm talking about the null hypothesis for this test. So for each of these tests, here we have an augmented Dickey-Fuller test, which is a typical test you would use to test for a unit root. And we're going to put in the levels data y of 1. And then down here we have a KPSS test, which is a typical test for stationarity. And again, we're going to put in the levels data y of 1. Now, we could just run this with all of the defaults for the tests, but what I want to emphasize is that it's very important when running these tests to take a look at the different parameter settings for the test to make sure that you're coming up with reasonable alternatives to test against so that you have informative inferences that you draw from these things. So if we go back and we just look at this data, although it does seem to be trending upwards over this 40-year period, more or less, these are interest rates, and we don't expect them to trend upwards forever. We do expect they're probably going to come back down and go back up over time, but stay around this sort of mid-range of about 8% that we see in this data here. So if we want to test for a unit root, we probably don't want to use an alternative that is a trend stationary data with a deterministic trend. We probably want an alternative like an autoregressive process with maybe a drift in it. So that's what I've chosen here, thinking that this is not going to keep trending upwards. My alternative is going to be an ARD model, autoregressive with drift model, that will test against the null hypothesis of a unit root. And same thing down here. We're going to test the null hypothesis of y of 1 being stationary against an alternative that it's trend stationary. Okay, so let me just run this section of the code here where I strip off the variable and run these two tests, and we'll take a look at the results here in MATLAB. And you can see that for the test for a unit root, we get a 0 for a result. That means we fail to reject the null hypothesis. Remember, the null hypothesis is unit root, so there's evidence for a unit root. And you can see that the p-value is about 29%, quite a bit above the default 5% significance level that we set for these tests. You can adjust that significance level to whatever you want. And then when we go down and look at the test for stationarity, we see that in this case, the result is a true value, a logical one, which says it does reject the null hypothesis, in this case the null hypothesis of stationarity, and it does that with a p-value of about 1% down here. So these are consistent. These are consistently telling us that this data does have a unit root, that it's not, we can't reject the hypothesis of a unit root. We can reject the hypothesis that it's stationary. That seems to indicate that we've got an integrated process here, not a stationary process, which is what we want for doing a co-integration analysis. Now, just to get the order of integration, we can go ahead and difference the data. So here I'm going to, in this next section, I'm going to just run the same two tests, but now I'm going to, instead of putting in the levels data, I'm going to put the differenced data into both of the tests. And let's just run these two. Go back to MATLAB. And now, when we test the difference data for a unit root, we reject that. So it looks like the difference data, and you can see that the p-value here now is very low. It very strongly rejects null hypothesis of a unit root for the difference data. In fact, notice this warning. It says that the test statistic was actually so large that it was beyond the tabulated values, the critical values that are tabulated in the test. And so what the test is returning here is just the minimum p-value in the tabulated values here. So that's a very strong rejection. And the same thing down here for the stationary test. You can see that we're getting the same kind of warning that the test statistic was so large that what's being reported here is just maximum p-value. In this case, it's a maximum p-value because we have a left-handed test on the one hand and a right-handed test on the other hand. But the important point is that both of these are very strong, either rejections of the unit root hypothesis or a failure to reject the stationarity process. So this is exactly what we want. We have the short-term interest rate. We see that in levels, it appears to be integrated, but when we difference the data one time, well, we seem to get a stationary process. So this seems to be an I of one variable. And if you go and check the medium and long-term rates, you'll find something similar. So finally here, let's just look at the differenced data. Same data we had before, just differenced now one time, and it does look like it's moving along some stationary mean there around 0. We do seem to have some heteroscedicity that I noted earlier in the early 80s there in particular. But it looks like it might be reasonable to model this system as a stationary process. Now here's the turning point though in the analysis. If you observe this and you decide to go ahead and model your differenced data as a stationary process with some sort of ARMA model, for example, and it turns out that these variables are co-integrated, then simply treating this as an ARMA model in differences and an ARIMA model would be a misspecification. Basically, what you've done by differencing the data is you've removed the information about the levels, and all of the co-integration behavior is in the levels data. So you really want to, when you get to this point, you want to make some more tests and see if this data is in fact co-integrated. Because if it is co-integrated and you go on and just treat it as an ARIMA model, you're going to be misspecifying the process that produced the data, and you're going to resultingly get poor forecasts, etc. On the other hand, if it is co-integrated, then we have alternative ways to model this kind of data. That kind of co-integration testing is what a lot of these new features in Econometrics Toolbox for 11a are concerned with, both testing for co-integration and then helping you estimate the parameters in an appropriate model. Let me go back to my slides for a moment here and say a little bit about the first test we'll look at, which is sort of the older, more classic test for co-integration called the Engel-Granger test. And the way it works is very easy to describe, which is one of the reasons that many people continue to use this. It's an easy test to understand. You start with your data in matrix Y there, just like we have, where the rows represent observations and the columns represent the different variables. And then what you do is you pick one of the variables in this co-integrating regression here. I've just stripped off the first column, and I say that first variable is going to be the regressand, and I'm going to use the remaining variables as regressors, and I'm just going to regress the first variable on the other variables. I may include x times a term in the model, deterministic terms, like I might want to include an intercept or a deterministic trend or something like that. And what I'm going to do is I'm going to form this regression and then look at the residual series. Now here's the logic of the Engel-Granger test. If I look at that residual series, imagine more or less solving this equation, the regression equation, for E, and throwing everything else on the left-hand side. So I'd have the first variable minus this linear combination of the second variables minus whatever intercepts and so forth I have equals E. If that residual series turns out to be stationary, then that would be evidence that the linear combination of variables that I found in B by the regression with a coefficient of 1 on the first variable, kind of normalizing the first variable there to have a coefficient of 1. If I have a stationary process on the right-hand side and on this linear combination on the left-hand side, that means I found a linear combination of the variables that's stationary. And then I can read right off the regression results, just a simple multivariate least squares regression here. I can read the B, and that will give me my co-integrating relationship. Now here's the twist, and here's a common mistake that people often make with this test. You want to take the residual series that you get from performing a regression like this and put it into a unit root test. But you have to recognize that what you're putting into the unit root test is not an observed series like you typically do with something like the Dickey-Fuller test that we just looked at. What you're putting in is an estimated series. You have these estimated residuals that are the result of a regression. And it turns out that if you put this into a Dickey-Fuller test, you can use the same test statistics as you would, but the distributions of those test statistics change. I've certainly seen people who say they're doing an Engel-Granger test where they take the residual series from a regression, put it into a Dickey-Fuller test, and take the results of the Dickey-Fuller test and use that to evaluate, whether or not co-integration is present. That's a mistake. You have to use new distributions for the test statistics that account for the fact that the series that you're testing is estimated. And that's what we do in the EGCI test in Econometrics Toolbox. We have the proper distributions tabulated, And so you want to use that. That function will call Dickey-Fuller or the Phillips-Perrin test or whatever you want to use for a unit root test to compute the test statistic, but it will then use the correct co-integration distributions for the Engel-Granger test to draw the inference about whether or not co-integration is present. Okay, so it's easy enough to run. Here's the EGCI test. And what we're going to do is put in our whole matrix of data here. So this includes our three variables as columns. And just to show you that we can run multiple tests with a single call, I'm going to compute two different test statistics, the so-called tau and z statistics here, with one call to this function. So let's just go ahead and evaluate this cell. And what we see here is that we get kind of mixed results. On the null hypothesis for the Engel-Granger test is that there is no co-integration. So if I get a 0 here, it says it fails to reject no co-integration. So that's not evidence for co-integration. On the other hand, if you look at the p-value, you can see it just missed. At the default significance level of 5%, this is just a little over. If we had set our significance level at 6%, this would have rejected the null of no co-integration. In other words, it would have provided evidence for co-integration. On the other hand, if we use this other test statistic, which is typically used in Dickey-Fuller tests, we get, rejection at a 2% level here, rejection of the null of no co-integration. So it seems like there's some evidence here, at least, that these variables might be co-integrated. Now, once you've determined that there might be co-integration among the variables, you might want to actually look at what is the relationship. We can just pull out that that vector of regression coefficients b that we saw earlier on the slide here, this coefficient b from the regression, which is performed by EGCI test. That's available in an optional fifth output argument from EGCI test here. We can just pull it out and then pull out the intercept and the regression coefficients here. And then I can form the linear combination in the regression, and I can plot it. So if I just go ahead and I do all of this, we get a plot of a new variable, which is a linear combination of the three interest rates that we started with. And it does indeed look stationary, more or less. It does seem to revert to a mean around 0, and although we see some volatility clusters, I suppose, at different points in time, it seems more or less stationary. So again, evidence that there may be some co-integration here and that we've actually found a co-integrating relationship. Once you've found a co-integrating relationship, to create a model that takes this into account is pretty straightforward. The model that we typically use for co-integrated systems is something called a vector error correction model, or in the case of co-integration, we usually just call it the co-integrated VAR model. So it looks something like this. You work with the differenced data on the left-hand side. So this would be for I of 1 processes like we have. This would be stationary variables. And let me just skip this term for a moment. Over here, we have a sum of lagged differences. So again, stationary variables. This is your typical VAR model in differences. So you can choose how many lags you want to use here in your model to capture the dynamics of the process. That's another topic altogether about how to pick that value for Q. But you're modeling the differenced Y data in terms of lagged differences here, and you're basically just throwing in all of the variables as regressors for all of the other variables. That's how a VAR model works. We can also include deterministic terms like time trends or seasonal dummies or interventional dummies and so forth in a deterministic term over here. What makes this model unique is this one term here that would not be stationary if these variables are integrated of order 1. And this is called the error correction term. It works with the levels, the lagged levels of Y, which would be integrated. And this coefficient, this matrix coefficient of lagged Y, in the presence of co-integration, this will factor. and it will factor in a non-unique way, which is one of the issues with co-integration analysis. What you're going to get here is two matrices, A and B, of both of the same size. They'll be n by r, where n is the number of variables that you're dealing with, 3 in our case, and r is the rank of this coefficient of the error correction term. So it's going to be a matrix, and you compute its rank. If the rank is full rank, then what you get here is an error correction term where you have a full rank matrix, and you can conclude that the process is stationary in levels. You can just solve for that error correction term, put all the stationary terms on the left-hand side, and you can conclude that your original data was stationary in levels. Not very interesting. On the other hand, if the rank of that coefficient AB prime is 0, then that term just drops out and you get a VAR model that's stationary in differences. The co-integration case, the interesting case, is when you have a rank that's somewhere between 0 and n, in our case between 0 and 3, where you get this factorization, and you can interpret the columns of B as being your co-integrating relationships. There may be more than one, and then the A's, the values in the matrix A, are going to tell us something about how fast the model adjusts to disequilibrium. If you think of the B prime times lagged Y as giving how far the model is from this stochastic trend, this stochastic equilibrium at time t minus 1, then we use the A to give the speed at which the spread adjusts and comes back to the stochastic trend. So that's a very brief introduction to co-integrated VAR models. But what I want to point out is that once you've determined the B, say you have a co-integrating relationship, which we just did here, and you come back here and now you know what B is here, now you just have pretty much a least squares problem for estimation. If you didn't know what B was, then you have this problem that you have to estimate A and B separately, and you know that's a nonlinear problem because of the product, so you wouldn't be able to do that with least squares. But if you identify B first, then you can go and solve for the rest of the coefficients in the VEC model just using least squares. I'm not going to go through all of that since that's not really co-integration analysis, but I will point out that we do that in our documentation. If you look at this section of the documentation, I'll just show you what it looks like. Here in Econometrics Toolbox, under the User's Guide, there's a section on multivariate time series model and a new section on co-integration and error correction. And if we go down here to the section on single co-integrating relations, like we've just looked at, there's this example that I've been talking about, where we identify the co-integrating relation, and then we plug the B into the error correction model, and we pretty much use least squares to solve for the other coefficients. That's this code here. You can take a look at it. It's really just a call to the MATLAB / operator to find the least squares coefficients, and here are the coefficients of your vector error correction model. So that's just basic least squares in MATLAB to get the rest of your coefficients in the error correction model. Once you've got that, of course, once you've got your error correction model, you can go on and do simulation and forecasting, and there's some discussion of that, how to set that up for an error correction model here. And here we do a little bit of a forecast forward using the error correction model. Okay, so that's all very straightforward estimation, least squares estimation, simulation, and forecasting once you've identified the co-integrating relationships in B. Now, there are some limitations of the Engel-Granger test, and just point that out here. The problem with the Engel-Granger test, or one of the problems with the Engel-Granger test, is that we arbitrarily almost always arbitrarily have to pick one of the variables to be the regressand and the other variables to be the regressor. And we might expect that the B we get, and maybe even the inference we get from the test, will depend on our choice of this first variable that we're going to put on the left-hand side. And indeed, that's the case. If you just do a permutation of the variables and run the Engel-Granger test for each permutation of the variables, That's what I'm doing here. You can take a look at this code more closely later, but it's essentially just running the Engel-Granger test with each of the three variables as a regressand and then regressing it against the other two. Let me go here to MATLAB and show you that we get different results. In two of the cases, we reject the null of no co-integration. That means we have evidence for co-integration at about the 2% or 3% level. But if we pick the third variable as a regressand, this time we fail to reject the null of no co-integration. And although, again, we're only at about 6%, just a little bit above the significance level that we've set at 5%. So the point here is that we get different inferences depending on how we make that arbitrary choice for the first variable. And we also get different co-integrating relations. The first co-integrating relationship here is the one we found before. You can see that there are two others that we find by doing the same regression with the variables switched around in the other two ways that we can do it. Now, there's no guarantee with the Engel-Granger test here that we found three independent co-integrating relationships. There may be some linear dependence among, or even nonlinear dependence, some dependence among these relationships, and so you'd have to go and do that analysis separately. So the point is that the Engel-Granger test, although it's classic and nice and easy to understand, it has its limitations. It's limited to finding a single co-integrating relation at a time, and it does have this possibility where you could be drawing different inferences depending on how you make some arbitrary choices. Let's compare the Engel-Granger test with a more modern, more complete test. Actually, calling this a test is somewhat misleading because this is really more of a framework. This is something that has been developed by Soren Johansson. It's a whole framework for testing for co-integration, estimating coefficients in an error correction model, and even then testing hypotheses about the co-integrating vectors and the adjustment speeds. Johansson's developed this framework where you can do all of this in the same setting, test for multiple co-integrating relationships all at once at the same time, basically make up for all of the shortcomings of the Engel-Granger test and do a lot more. So we also have a Johansson test, a couple of Johansson tests in the econometrics toolbox, which by manipulating the parameters and values, you can carry out all of the different analyses that you would typically do in this Johansson framework. One of the things you're going to have to do when you're using the Johansson test is something you have to do in like the unit root and stationarity tests that we spoke of earlier. You have to pick an appropriate model to be testing against. And Johansson lists these 5 models, 5 types of co-integration here. They're basically just looking at this error correction term plus the deterministic terms in the error correction model. And Johansson lists 5 cases here that typically come up in econometric data, some of them not so typically, like H and H2, but he considers 5 cases, and our framework allows you to consider 5 cases as well for co-integration, depending on whether you want to include intercepts and time trends in the data as an alternative, whether you want to have intercepts and time trends in the co-integrating relations and so forth. So I won't talk a lot about the details of how you make that choice, but there's a lot more about that in the documentation, and you can read a little bit more about these different options for co-integrating relationships. As far as running this, though, it's very simple to run in Econometrics Toolbox. The Johansson test looks just like the Engel-Granger test. You input the levels data in the form of a matrix. You pick some appropriate model of co-integration. I'm going to pick Johansson's H1 model here. And again, just to show you that we can run multiple tests in one call to the data, I've picked 2 different lags for the error correction model. Remember, that's the Q. The Q here is the number of lags in the error correction model, something that you want to choose. What Johansson's test is going to do is it's going to test for co-integration, but at the same time, if it finds that there's co-integration with a certain constraint on the rank of that error correction matrix, it will estimate the error correction model with each of those ranks. So let's just run this cell, see what the output looks like. And you can see it's a little more descriptive than what we got for the Engel-Granger test. We've got two results summaries here for test 1. This is the model with 1 lag in the error correction model. And down here is the results summary with 2 lags for the error correction model. And this table here summarizes the results. We consider the whole range of cases for the rank of that error correction coefficient, 0, 1, and 2. Again, rank equal 3 is not an interesting case. That's full rank for it. That means that the data is stationary in levels already. And you can take a look here at the p-values and so forth, but what we've decided here is that it's going to reject the null hypothesis of co-integration for rank 0. So that's pretty much no co-integration, because that would mean that matrix has rank 0. It rejects rank 1, but it fails to reject rank 2. So there's some evidence here that there is co-integration here with a rank 2 matrix for B, meaning that there would be 2 co-integrating relationships that this test has found. If we change the model a little bit, you can see that our results are a little less conclusive, a little less informative. They fail to reject any of the ranks. Could be 0, could be 1, could be 2. The statistics fail to reject that. So there's some evidence here. You can play around. I mean, this is just good evidence that it's important to pick an appropriate model for your data. Play around with the lags a little bit and look at the evidence here, but it does look like there's some evidence for maybe 2 co-integrating relations in the data. Now, just like the Engel-Granger test returns that reg structure as an optional fifth output, the Johansen test is a maximum likelihood framework. The way it does its estimation and testing is not through least squares, but through maximum likelihood. And the MLEs are returned in a fifth output. And what I'm going to do here is these won't be computed unless you actually ask for this output. If I do, and I'm just going to turn on a display here parameter to actually show the estimated parameters. We'll look at this lag 2 model that we looked at earlier. And what you're going to get is this MLE's structure out. And if you want to get things like the B matrix that includes the co-integrating relations, you just index into it using a syntax like this. This is all documented in terms of the field names in this structure, but just MLEs.R2 for rank 2 if you want to get the matrix for the rank 2 case, paramvals.b. So I'll run this, go back to MATLAB, and what we have here is here's the test again that we ran. And in this case, we asked for that MLE's output, and we had the display on. So here are the coefficients in the VEC model for the rank 0 case. Now remember, rank 0 means there's no error correction term, so there is no A and there's no B. What I've got here is these are the lag delta Y's at lag 1 and lag 2. And here's my intercept term in my VEC model. In the case of rank 1, well, now we have 1 column for A and 1 column for B, and the product AB prime then is our error correction coefficient. And here are the values for our lagged coefficients. This is the intercept term, and then we also have the constant that's included in the co-integrating relationship that we estimated by default here. You can choose the model that you want, one of Johansen's models, to either include that or not. And then finally, the rank 2 case, now A and B both have 2 columns representing 2 co-integrating relationships, and these are the coefficients of the corresponding VEC model for modeling those 2 co-integrating relationships in the data together. So you can see already that this is much more powerful than what you can do with the Engel-Granger test. You can evaluate all the different possible ranks for the error correction term and estimate them in one call. You can estimate the model for each of those cases and get your coefficients and compare. Finally, let me just say a word about some additional tests we have. We have a function called jcon test, which allows you to put constraints on either the co-integrating vectors or the adjustment speeds in the error correction model and test to see whether those constraints are supported by the data. Just to give you an idea of what I'm talking about here, imagine that we're working in a case where our matrix B of co-integrating relations is n by r. So remember, n is our number of variables. It would be 3 in the case of our interest rate data, and r is the rank of the error correction term and the matrices A and B. It represents the number of co-integrating relationships that we've found by testing. So typically r is going to be less than n in the cases of co-integration, and if you look at the columns of B, the vectors that represent the co-integrating relationships, so here I've got the first column and the second column, they're going to span, these are going to be n-dimensional vectors, but they're going to span a subspace of dimension r in n-dimensional space. And the issue is that the estimates for A and B depend on how that factorization of the error correction term is done, and it's non-unique, and you can do it in an infinite number of ways. So it may be that you run this test, you get estimates for the co-integrating relationships, but they're hard to interpret in terms of, say, the economic data, the economic situation that you're trying to model. So you might want to ask the question, well, is there another co-integrating vector that actually makes sense based on economic theory that lies within the subspace that's been identified by the Johansen test? So I've just indicated two other n-dimensional vectors here, one in green that does lie in the subspace spanned by our co-integrating vectors, and one that does not. And that's the kind of thing that jcon test looks like. It'll allow you to make inferences about questions like this. Does this particular vector, suggested by theory, say, lie within the space of co-integrating relations that has been estimated or not? And there are also versions of it that will allow you to look at linear combinations, put constraints on certain linear combinations of the variables have to be true, purchasing power parity or something, where you have one variable is equal to the sum of two others. Is that constraint satisfied in the subspace of co-integrating relationships? You can test all of those kinds of hypotheses on both co-integrating vectors and on adjustment speeds using this function jcon test. So just to illustrate and to wrap up here, I'll check something that we've already checked. I'm going to look at each of the variables individually by just giving these indicators here, three, and I'm going to run 3 tests to see, is this a co-integrating vector? Is this a co-integrating vector? And is this a co-integrating vector? Now look at these vectors. These are putting a 1 on one of the variables and 0 on the others. So if it's a co-integrating vector, that means that combination of the variables is stationary, which means in this case, variable y1 is stationary, variable y2 is stationary, and variable y3 is stationary. That's what we're testing. Basically, we're doing the pre-testing that we did earlier to see if we're working with stationary or non-stationary data within the Johansen framework. So you don't really have to pre-test. You can do it within the same framework. It's another nice feature of what Johansen has worked out with this framework. So if we run this, go back to MATLAB, we get strong evidence of what we already discovered. There's strong rejection of each of these 3 hypotheses that the variables individually are stationary, and you can see the p-values are quite low. So we get rejection of stationarity. We found that earlier, but we were able to do it for all 3 variables at one time, and we were able to do it within the same framework that we're using for testing for co-integration and estimating our model, which is really nice. Okay, I think I'll leave it at that. I hope that gives you a little taste of some of the new things we have for doing co-integration analysis in Econometrics Toolbox, and I hope that you'll go and have a look for yourself.
Okay, so what Bill showed you is how to perform co-integration modeling and analysis using the feature set from the Econometrics Toolbox. Now what I'd like to do is show you an example application of using co-integration that often arises in trading. This is often called pairs trading or sometimes spread trading. So one way to think about co-integration is that you're looking for that long-term behavior between two price series. You could think of it as interest rates, as Bill showed earlier, or you could also think of it in terms of the price of Coke or Pepsi. When you compare the price of Coke and Pepsi individually, those firms have different prices when you look at them at any given time. But over the long term, since they're both from the beverage sector, they both respond to the same economic situations. If consumers are not buying beverages, they both take a hit. If consumers are both buying beverages, then they both climb. Now, that's an example. You can also think of an example in the automotive industry, such as GM and Ford. The recent downturn in the automotive industry might be reflected in that both GM and Ford price behavior might have declined over that region, even though Ford might have grown more than GM in the current situation. You can take a look at that long-term trend and determine whether or not there is a co-integration relationship. So that's what we're going to do here, but we're going to focus on the spot price of oil, specifically so we're going to take a look at two different prices. One is LCO, or light crude, and then the other one is West Texas Intermediate. So the plot here is the current price, or spot prices, of those two price series. And one thing you can look at is they do look like they behave similarly, much like the interest rates before. So our goal here is to take a look at this and identify whether or not these series are co-integrated, and if they are, use that information to develop a pairs trading strategy. So really the key task here is to identify that co-integration relationship. Does it exist? And if it does, take account for that within the strategy. So let me go ahead and move to MATLAB, and we'll go ahead and take a look at this example. So like Bill did earlier, I'm going to run my example from a prepared script, and this script is going to walk us through the pairs trading strategy. So the first thing we're going to do is go ahead and load the price series for LCO and WTI and create a plot of that. So these are coming from a database, which happens to be contained within the data folder. They're minute bars. So one thing you can look at is the price series over time between these two. And if you look at time series before 2011, it looks like they tend to track pretty closely to each other, with a small divergence here, a little bit of divergence around here, and then more recently you're looking at a wider divergence between the two here. So one question is are these series co-integrated? And in particular, if you look at this recent trend from roughly before 2011 and onward, are they co-integrated, or will they continue to be co-integrated? So one could hypothesize that these two will then revert back to each other and continue to track, if you believe that's the case, but there may be economic situations that are driving the divergence of these two. So what we really want to do is test this time series for co-integration. So what we're going to do is we're going to look at the past 11 days in this most recent divergence to see if they're co-integrated. So, but before I do that, before I run the Engel-Granger test on just a subsample, let's go ahead and run the Engel-Granger test across this whole time series and see if the price series are co-integrated. So we're putting in the closing price or the closing spot price of LCO versus WTI as inputs into the Engel-Granger test. We run that, and what you can see is that it comes back with a true. So essentially it's saying there is a co-integration relationship across the entire time series. So it might be interesting that you might be thinking that in the longer term that these two are going to tend to grow back towards each other and tend to trade in very similar ranges. But if you don't believe that's the case, and you want to just test over a smaller time period and see if they are still co-integrated, such as over this range, we can do that. And that's what we're going to do over here. So we're going to basically break out the past 11 days, take a look at that data. So you can see the 11 days broken out here. And then we're going to test this data and see if the data for the past 11 days is still co-integrated. And that's what we're going to do within this cell here. So we're going to test that series, which is a subset of the original series. So we go ahead and test. The Engel-Granger comes back and says it's 0, and that 0 indicates that we cannot or that 0 basically rejects the null hypothesis that there are no co-integration relationships. So it says that they are no longer co-integrated over the past 11 days. So if you're looking to develop a trading strategy on this, you'd have to make the assumption that they are going to revert back to a similar behavior before 2011. But what I really want to do is take a look at the intraday data and see if there's a co-integration relationship given within an individual day. And one thing you can look at is, even though that these say that they're not co-integrated across the 11 days, we take a look at this time series, say here. So we'll pull out this day's worth of data, and we're going to test and see if it's co-integrated. And we can also pull out the next day's worth of data to see if it's co-integrated over this time period and so on. So what we're going to do is we're going to go ahead and do that, essentially for the series from 1700 to 2000. So we're going to go ahead and look at a range of data in here, basically about a day's worth, maybe a day and a half worth of data, and see if there's a co-integration relationship. So we go ahead and do the test, and you can see that the hypothesis test comes back as true, indicating that there is a co-integrating relationship over a single day. That's a good incentive that possibly we could do an intraday trading strategy, pairs trading strategy on this time series. And so that's what we're actually going to look at now, is can we develop an intraday pairs trading strategy on this time series, even though that given over several days they may no longer be co-integrated. They do have periods during a given day where they may be co-integrated, and can we take advantage of that and develop a trading strategy based upon that information. So this next cells, what that does is it's going to just display the co-integration relationship. So it's returning that relationship that was there, where the coefficient is, the standard errors, the R-squared value of the co-integration relationship. If we wanted to get a feel for the coefficients, so this would be the slope, but this is kind of the scale. They would be inferred between these two. So if you're developing a trading strategy, you want to take the co-integration relationship into account. And what we're actually going to do is we're going to plot this co-integration relationship over time and see what are the right coefficients to use and develop a trading strategy for that. So just to graphically explain what we're going to do before I talk about the pairs trading strategy, let's go back to my slides real quick. And what we have here is basically the solution that we're looking at is if you look at this blue line, this is that co-integration relationship. So we're basically plotting that co-integration relationship described by those coefficients. It tends to average around a certain value. In this case, it looks to be around 0. And one thing you can look at is if it's above 1 or below -1, this indicates an overbought and oversold condition with respect to LCO. So we look at this situation, anytime we're above here, LCO is assumed overbought. So it's a good time to sell LCO and buy WTI. So that's the pairs trade that's going on. Anytime that there's a transition between this region and the next, that's a good indication that you can do pairs trading. But the other thing to look at is during this trend is that spread, or the co-integration relationship, is showing you that they do tend to diverge for a while and come back towards a mean value, which happens to be in the co-integration relationship about 0. So we're looking at using this co-integration relationship along with an overbought and oversold condition, which is pretty common practice when you're looking at a mean reversion strategy for trading. So that's the example we'll be using, is rather than using this actual spread between the two, we're going to be using the co-integration relationship, because the spread may or may not actually give you a good buy and sell relationship versus just the spread, because the spread could be misleading and indicate buy and sell conditions when they're really not there. So let's go ahead and go back to MATLAB. So I'll go ahead and open the pairs trading script, which is essentially describing the strategy that we're going to work to. So you can see that pairs takes in the series and two input parameters, M and M. If you look here, what we're going to do is we're going to pass in the window. So the first parameter is the number of time points that we're going to trade against. So this is the window of data we'll be taking in and developing a pairs trading strategy against, 420 minutes in this case. And then 60 happens to be, or what's the maximum number of periods that we're going to use to estimate the co-integration relationship. So in other words, if you look down here, it discusses for every n periods, we're going to use the previous m periods worth of information to estimate the co-integration relationship, if one exists. So one thing to note about this pairs trading strategy, if it doesn't exist, it won't trade. It's only going to say when one exists, we'll actually be doing trading. So within the for loop here, what you can see is we're actually doing the test for co-integration over that time period. So we're testing if it exists, only engage in trading when we reject the null hypothesis. So essentially what we're looking at here is compute the residuals over n days, And then, if the residuals are large and positive, then we're going to first enter into that trade versus the other. So the first one will likely decline, the second one will likely rise. So we're going to short the first and buy a scaled number of the second. And then we'll reverse that in the other case. And then we're just basically going to calculate the return and the Sharpe ratio. And the Sharpe ratio as a measure of the performance. So what we're going to look to do is maximize the Sharpe ratio a little bit later. And then this also will plot the results. So let's go ahead and run an example using a window of 420 and 60 minutes is the maximum size to test. So we go ahead and run that. And what you get is this plot here. So you can see for a strategy of rebalancing every 60 minutes with up to 420 minutes worth of data, you can get about a 7.74% return in this example. And if we zoom in and take an example look at when some of the first trading begins, what you can see is that we have an indicator for the position of WTI, position for the LCO. We're going long one, short the other, and then they change. You can see how often we trade throughout this entire strategy and how profitable it is. And also take a note that when it determines that there is no co-integration relationship, that it is not trading. So what we have here is a situation where a co-integration relationship wasn't found, so we're not entering into a trade. It won't do it until it finds one. So what we're basically doing is looking over this window, whatever that window is. We still need to determine what the optimal window is. But over up to 60 minutes, if no co-integration is found, we're not going to trade. It's only going to trade during the time periods where we do have a co-integrating relationship. So now what we need to do is find out what those optimal parameters are. So what we're going to do is we're going to actually run a backtest or a parameter sweep to identify what these are. So I'm not going to go into the details of the parameter estimation or the parameter sweep that we're doing here in the interest of time. This whole framework was developed during the algorithmic trading with MATLAB's webinars. So if you're really interested in that, I recommend you go see those webinars. But I'll give you a real quick overview of what we're doing. So this first command is going to open up a MATLAB pool, and this is essentially to run each one of those parameters on a different worker if we have one, a MATLAB worker. You can see here that I have an indicator that says 8. And what this is telling me is that MATLAB is open with 4 pools, or with a pool of 8 workers on my current laptop. So this laptop has 8 cores or 8 workers available to it. We're going to dispatch the parameter estimation problem across those 8. The next thing we're doing is we're setting up the range of parameters for the window, which ranges from 120 minutes to 420 minutes. That's the maximum size, which will be 10 to 60 minutes that we're allowed to use, and we're putting that in a range parameter. Now the annual scaling and costs are entered into the pairs function, is just, but we'll go ahead and look at this. So what we're doing is testing if there's scaling, if there's cost, providing defaults exist. So what we're essentially calling the pair strategy. So the function handle here basically is allowing us to pass in a function to another function. So we're going to pass in this p function to this other function called parameter sweep. Now parameter sweep, what it does is it takes the input range for both windows and frequency as well as a function, and it runs it over every combination of those points. So what this does is this is essentially handles or encapsulates the multiple for loops you might have to do to run over the entire range of all these different parameters. And this function is the function that's been accelerated using parallel computing. So what we're going to go ahead and do is run this, and at the end this function pulls out the best parameters. So it's going to take those input parameters to our function, and it's going to do it so the parameters are selected based upon maximizing the Sharpe ratio. So it's going to find the maximum Sharpe ratio, and that's what it's going to plot here at the end. Let's go ahead and run this. This should take, I think, roughly about 30 seconds to complete. So what we're doing now is we're testing that pairs function over all the different combinations. And once it's done, we'll then see the plot come up of the best pairs trading strategy based upon the window that we've found. Okay, so you can see that it's done, and here's the plot. So here's the original price series. So we're looking at the past 11 days worth of data. We're looking at rebalancing every 40 minutes with 180 minutes worth of data as the window. So if you take a look at this, what we're doing is the previous one I put in 60 and 420 as the parameters. The parameter sweep is identified based upon the Sharpe ratio maximization, that the best combination would be 40 minutes with 180 minutes worth of prices. So essentially you'd like to rebalance the pairs trading strategy, and have a moving window of about 180 minutes. And if you do that, what you look at is you get the performance like this. You can see that there are periods where there is no trading, no co-integration relationship was found. The pairs trading strategy just wasn't viable based upon the current information within those price trends, as well as here. But you can see that there are days or periods within each day that there are a co-integration relationship that we can then test over and trade against. And you can see the trading information here for both signals. If we were to actually trade this based upon that cost, which was 0.01 shown before, which is roughly the bid-ask spread you would see between buying and selling these, what you end up getting is about an 8% return, about 7.9% return actually. So you get an 8% return over a couple days worth of trading, which is not too bad. So if we return back to the slides, just to summarize, what we used for the solution really was basically using the angle-Granger test to determine when co-integration occurred, and then using that co-integration to, as an example in this plot, to determine when to buy and sell. So we're actually plotting our trading strategy against the co-integration relationship. So in essence, the co-integration relationship became our indicator, and then we just came up with an overbought or oversold condition. And then you saw the performance of that. So that basically wraps up all the time we have for today, and what I'd like to do now is essentially move into the question and answer session of this webinar. So what I want to do is remind you, if you haven't, please post your questions to the Q&A tab, and we'll do the best to answer them starting now. So the first thing I'm going to do is I'm going to go quiet for a few minutes while we switch over so that I can start reading some of the questions, and I'll be back shortly to start answering them.